Hi, everyone. Thanks for joining us. My name is Bayo Rov-Ikpah, and with me to present our project for the EE611 Emerging Threats and Defenses course is my coworker Gabriel Miller and Samuel Newton. This is our presentation for the fall semester at the University of North Dakota, the EE611 course, and the title of our project is Machine Learning-Based Dynamic Threat Intelligence and Cyber-Physical Systems. Next slide, please. So our outline for the presentation is our introduction. We'll talk about our methodology. We'll look at our results, as well as future work and recommendations. And finally, we'll look at our conclusion. Let me hand over now to my colleague, Gabriel Miller. Gabriel.
Yep, so our overall work is and demonstrating how we can use machine learning to dynamically protect a production environment. The idea is we are identifying new threats and emerging threats, and we are able to protect a production or enterprise environment from ongoing threats that we are gathering from our honeypots and we're analyzing with our machine learning method. So within our methodology, we started with a high-level architecture. You will notice here that items in red are essentially untrusted. Both the enterprise environment, the honeypot, the attackers, and the firewall decoy. The green items are for machine learning, the forward analyzer, which is our syslog, the production firewall, and the SCADA environment. And again, green is considered trusted. So kind of our categorization there. You will notice that we also have the production environment kind of boxed off and kind of guarded here to kind of represent where our logical devices lay within our environment. So within our project, we try to kind of follow the methodology here of the numbered scheme where we start with the internal attackers. We work through our various systems through the honeypots. Gather our logs, send them to the syslog, allow our machine learning model to program our firewall, thus protecting the SCADA environment. Once we determine that the attacks were successful in training our machine learning algorithm and updating the firewall, we then open it up to the public attacker, which is number 5 there, with the idea that we would have additional information for attacks that we couldn't accomplish internally. And that in turn is going to protect our production and SCADA environments, which essentially is listed at number 6, respectively. So with that, we decided to use the Forward Deceptor as the decoy deployment environment. So actually what we have here is a high-level dashboard of incidents, lures deployed, which is essentially services, operating systems, and essentially a timeline. And you'll notice in that timeline that we have spikes, and the reason why that is we're running the program internally. We're running attacks against the program internally for those ones. And then you'll notice the second spike there. Essentially, we had a spike and it never went back down to 0. And the reason why that is because we then opened up the production environment. I shouldn't say production environment, excuse me, the honeypot to the outside, which then allows the attacks to occur essentially all the time. So that is why that line never goes back down to 0. So kind of a quick high level of the Forward Deceptor environment beyond the dashboard. I'm going to go ahead and open this up here. And you will see that we have our various decoys deployed. And within this environment, you will see that we essentially have our deception operating systems, which is essentially our decoy. Unfortunately, this environment, we couldn't run multiple at a time. But the idea here is, depending on the use case, you could run various operating systems. And within these operating systems, they offer various services. For our demonstration purposes, we chose to run this middle one, which is just an Ubuntu system. And for it, we had multiple operating protocols available. And the idea here is we were training our deception model. So these are the decoys we were running. This then allows us to do some analysis on the attacks. And you'll notice here that because we open this up to the public interface, essentially the internet, you will now see that we've got various countries and attacker IPs hitting it from multiple countries. Probably the most concerning one, Russia. And I'm trying to find some other ones in here, but just kind of a highlight here. It's from everywhere, essentially across the globe here. And then this particular review, and it's going kind of crazy at the moment, will essentially lay out a distribution of where all the various attacks are coming from. It tries to color code it for you. You'll notice all of these are public IP addresses that have shown up since we've opened this environment up to the internet. So effectively, this is representing all of the attacks that are occurring within the environment. So with all of this data, this analysis is then sent to our aggregator, our syslog. This data is then sent and analyzed by the machine learning algorithm. And effectively what that does is it will train our machine learning model to generate our code, which I will now hand this off to Bayo, who will kind of explain what we did with that methodology and how we applied this data to that machine learning.
Thanks, Gabe. So our methodology for the machine learning, first of all, we had to go through the steps for any machine learning algorithm or implementation. First of all, we have to collect the data. So data collection is one step, and then we have to prepare the data. We have to pre-process that data, make sure that it's clean. It's not, with any errors or missing points. I mean, some good algorithms can fit the missing points, but we had to make sure that our data was ready for the machine learning algorithm. We selected a random forest algorithm, and some of the reasons why we did that, we found out through research that random forest has high accuracy and robustness. It is versatile as well as scalable, and it is proven to be quite effective. We can dive deeper into those details as we explain our slides. Also, when we're done with the selection of the model, which we did for random forest, we have to evaluate that model and then tune the parameters, do the predictions of, in this case, attackers or whatever targets that we decide to use. In our case, we chose attacker IPs or what type of events. We did play around with quite a few, but for the purpose of our presentation and report, those were the two that we settled with. And then we deployed the model in an example environment of a production environment, which is the smart grid based. This, however, can be utilized for several other production environments. Now, on the left side, we can see we get the training set into the random forest as well as the test set split. The training set is taken into the algorithm through several nodes. And then these nodes then move it onward to the decision tree nodes. Decisions are made by some classifier, and then it gets aggregated upon. There's some voting that is done, and then after that, predictions are made. The random forest classifier uses an ensemble model to do its classification. And we could see on the right side, we have the original data, which is multi-dimensional. It has a lot of features, which you can see is color-coded. And then we have the nodes in the next layer. We have different classifiers, and then they have their own rules. So they make some decisions, and then they output, kind of like a logic state in the output. If it's true, goes in one direction. If it's false, goes the other direction. Um, and this uses a process known as bootstrapping as well as aggregating. Random Forest also uses bagging, which makes it really versatile when it comes to when you don't have too much data or known data. If you're doing some training of something quite new, you could do you use the data with replacement, so it can recreate certain data sets with the original data that you already have. Next slide, please. Okay, so we will be looking at our code that we use for the deployment of our machine learning. And this window right here, we use Google Colab as our IDE for Python, rather Python IDE, and we use Google Colab to deploy our code. So you could see the first step that we did is to import the required packages. So we load those packages, and thanks, Gabe is helping me to run them line by line. You can see we load the data sets. This is from Google Colab. We have it on the cloud. And then we do the pre-processing of the data. So we filter the data so that we can have them just, it's not dirty, but clean for our machine learning model. And then we have a label encoder. This label encoder, um, random forest works with numbers or logic states, either 1 or 0, true or false. We have to get it into a format that it can recognize. So the label encoder helps us to do this, to set states, preset states that the classifier can work with. And we split it. We split the data into the testing set as well as the training set. So in this case, you can see we have 30% of test data. That means we have 70% of the data will be for training purpose. And then we then deploy, or we call, the random forest classifier. So we have a variable and we call the random forest classifier, and then we put the number of estimators that we needed to run with. In this case, is 100. We did some tuning of those hyperparameters. So those n estimators, those are the nodes that will be making decisions in the decision tree. So in the next line, and we deploy that. And then we evaluate our model once it's gone through to check our accuracy. You can see the accuracy for the service is 98%. And that was a really good score. We did tweak and tune, and then we got different, but like this was one of the good ones. And then we do have our classification report, the detailed classification report for the ensemble metrics. I will at this point hand over to Gabe to walk us through the rest of the code.
All right, thank you, Bayo. So essentially what we have here is we are now having to filter the data per the Fortinet syntax. So this essentially is two separate sets of code, so to speak. This next piece is essentially running service patterns. So it is basically pre-prepping the data so that we can run it directly on the firewall by SSH. And effectively what you have here is the patterns of what it should look like when it gets to the firewall. So that is for the service. This next section is for the patterns with the IP addresses. So you'll notice here that it's putting it in the correct format for IP addresses. So these are actually attacker IP addresses that it's currently seeing on the network. So that is kind of why you see that occurring here. And then this next section effectively is signing in the code to the firewall. So it's signing into the firewall. It is applying the actual code to the firewall per syntax for this particular firewall vendor. So I will go ahead and let this run. It does take a bit of time here to run through, but what you will see down here at the bottom as we run this is it is actually running the code on the firewall. So based off of our machine learning outputs here in the predictions, you will see that the attack IPs are now being applied to the firewall. And as it kind of runs through the selection here, you'll see that every single IP is being applied as an address object here. And the idea is that once we have all the objects on here, we can then dynamically apply the firewall policy. So as this kind of runs here, again, you can kind of see the methodology and the order that it has to apply these. So as these run, you will see it kind of go from various section to section. These are currently in the address object section. It looks like there's actually quite a few here since we've last run this model. So it is essentially learning and doing its job of keeping this list up to date, so to speak. And then eventually what we will see in here is a group. It will take these objects and will dynamically put them in a group for the firewall. So it's a matter of applying them to a group and then to the firewall policy. So as this kind of runs here, I'm going to go ahead and turn this back over to Bayo, and he will kind of go through our next machine learning outputs here, and we will go from there.
Thanks, Gabe. So we will talk about our results. This metric in this table kind of shows us for the random forest algorithm, we have our nodes, which is the n estimators, and then we have our train/test data split, which is a percentage of the data that is given as the testing portion of it. And then we look at the accuracy. So right there, you can see where we have 10, and when we have 10% of the data as a testing, we have 100% accuracy. Now, we kind of, that in a real world situation, you don't have that much test data, so that was not our optimal. We didn't choose that because of that reason. When you see the next line where we have 20 nodes, and we kind of bolded that, where we had 30% test split. We had a 98% accuracy, which was the next best after the 100%. And it's more like, achievable, more realizable in a real time decoy or production environment situation. So that was like our best optimal value. You could see with 50 nodes and 100 nodes, we have different accuracies that come forward. So this table kind of helps us to see how our model is performing. And with that, I'll hand it back over to Gabe.
Thank you, Bayo. So now that our code has finished running, we will kind of demonstrate what the use case was here. So this is kind of a snapshot of the firewall pre us running our machine learning code. And you will notice here that we are not identifying any external attacker IPs to prevent potential attacks from occurring. So the idea with this is that once this code is finished running, we can then go to our firewall, which is right here, and you will see on the production firewall policy sets compared to our previous snapshot, we now have a bad guys policy line here with an attackers group, which I walked through. There's all the attack IPs that have been occurring on the public internet as well as our internal. You see the associated services with them that it has learned. So with that, I will go ahead and hand this off to Sam to describe kind of the environment that we're actually protecting. So here you go, Sam.
Thank you, Gabriel. Well, so we are protecting the production environment. So the production environment is made up of the power plants. Actually, yeah. So the whole thing is made up of the production environment is the smart grid. So over here we stuck to the power plant. We are not dealing with the transmission and the distribution. We are dealing with the generating section or the generating part of the smart grid. So over here we have the generators that is connected through the generator bus to the transmission line to the load bus bar to the various loads. So we have 11 loads over here. We have 11 generators, and then they are linked through maybe wireless or through a LAN to the server. And then the server over here, since it's connected to the generating station, any attack that hits the server means you can control. If an attacker hits the server and takes hold of the server, he or she can control the generators or the power plants. And that is the main reason why we are trying to protect it. And then so that nobody can hit this part of the network, right? And moreover, the firewall, so this is the detailed illustration of the generators, right? Of the production network. So we have generators, 11 generators, we have 11 loads, we have cost, and then all this data was picked from NYISO with October 16, 2024 data was what we used to illustrate. So if you look at this is the data we collected, and then please can you click on the other one where I can can you show them the code? Yes, and so this is the code illustrating how we came about the final illustration on the left side. So on the left side, we have the data that was collected through the code. We're able to illustrate over here that generator 1 is connected to load 1 was connected to load 10, load 11, load 2, and so on. That is the unit commitment. And then generator 10 has load 2, generator 11 has generator 11 was also connected to load 10. Can you please shift it to the left, please? Can you shift? Yeah, so I can. No, yeah. Thanks. Thanks, Gabe. No, please to the left. Is that right? No, I want to comment on the, yes, thank you so much, Gabe. All right, so generator 2 was, load 10 was connected to generator 2, and then generator 3 was connected to load 6, generator 4 was connected to load 7, and so forth and so on. So this over here is illustrating the production environment, how everything is working without being hit by an external attacker because of the way we devise our network. So it's been protected. It has learned everything and is updating the firewall. So therefore, any attacker that comes, the firewall is able to learn and then protect this environment. Thank you. Over to you. So our future work, in the future, we require that additional features and methods will be implemented within the machine learning methodology, and also additional attack strategies can be classified and detected, such as signature-based attacks. Firewalls and cybersecurity will require less manual intervention to protect against the ever-evolving attack surface. Thank you. Over to you, Gabe.
Okay, thanks, Sam. So in conclusion, first of all, thank you all for hanging with us and learning something about our project. Based on this project, we've been able to demonstrate that it is possible for machine learning to operate in conjunction with honeypot deployment as an offensive method of cybersecurity defense. Firewalls and the associated cyber infrastructure can dynamically adjust to new and emerging threats. And also there is increased flexibility that allows for the application of our method in diverse environments. Once again, thank you so much for staying with us, and have a good one.